Hola a todos, bienvenidos al tercer y último día de la ENUAM Virtual 2021. Y es un placer para mí en esta ocasión presentar a nuestro segundo expositor de nuestras conferencias plenarias, al doctor Damián Pambambán. Voy a seguir en inglés por respeto a nuestro presentador. Here we are more than happy to have Professor Damián Pambambán with us to give this plenary conference named Sediment Transport Around Hydraulic Structures, New Challenge with Climate Change. Professor Pambambán got his civil engineer diploma in the National School of Public Works of the state in France, in Lyon. He also got his master's and his PhD in civil engineering and coastal engineering in Clonbernat University, also in Lyon. Right now, he's a professor at the Center of Haute Terre Environment of INRES, the Institut de la Recherche Scientifique in Canada. And he's the scientific co-leader of the Environmental Hydraulic Laboratory and the Multidisciplinary Computed Tomography Laboratory for Natural Resources and Civil Engineering. Before joining INRES, Professor Damián Pambambán was the director of the Hydraulic and Environmental Risk Laboratory, a component of CEREMA, is the Center for Studies and Expertise on Risk, the Environment, Mobility, and Development at the Saint-Venant Hydraulic Laboratory in the metropolitan area in Paris, France, where he worked several years as a researcher. He also was an engineer in CETMEF, the Center for Maritime and Fluvial Technical Studies of the French Ministry of Environment, Sustainability, Development, and Energy. The research work carried out by Professor Pambambán aims to better understand sediment processes in order to study current and future trends in the evolution of landscapes, including surface water. The work in progress concerns a better knowledge of the erosion processes near coastal developments. The work is also current in experimental computational modeling, as well as field observations. Just to point a remark, in 2020, Professor Pambambán was one of the 9 INRES professors to get more than 1 million in research grant for advance of their innovative work. Well, so welcome again, and you can start wherever you want.
Thank you, Mr. Chairman. So, buenos dias. I will share my screen now. So I'm very happy to be with you today. And I hope you can see my screen.
Yes.
Yes, thank you. So today I will talk about sediment transport close to hydraulic challenge structures. So my name is Damián Pambambán, and I'm co-director of 2 labs at INRS in Quebec, Canada. One is a big wave flume, and the other one is CT scan tomographic measurements for hydraulic and sediment transport. So my presentation will propose 3 parts. One is some background of sediment transport. Why is this important? What are the difficulties? In what, second part, numerical model can tackle difficulties? But what are the still remaining open questions? Also, the difficulty for making measurements and how inaccurate are sometimes measurements. And finally, I will illustrate with ongoing study in my lab about wave impacts on seawall in terms of impact forces, but also in terms of erosion at the top of the structures. So this first part is to give you some background, how important, how difficult is study on sediment transport nowadays, still nowadays, because it's a very old discipline. So a long time ago, researchers were interested in sediment transport because it changed river morphology, it creates river meandering. It also is a problem for a lot of human activities like fishing, harbor, coastal engineering, coastal erosion, coastal floodings, and so on. So this slide is just to give you a simple picture on the physical problems, but also the mathematical problems in terms of interaction between a flow with interface, which is sediment grain. So if the fluid flow is strong enough, there is a friction at the interface of the sediment bed and displacement of sediment grain. So if we have a granular scale viewpoint of the physics, we can compute the motion of one grain, one by one. And for each grain, there is the fluid-solid interaction are drag force, lift force like flying plane, and gravity, of course. So depending on the magnitude of the force, we can have different motion of grains. For low velocity, but strong enough for moving sediment, we can have the rolling motion, so the grain rotates, and like for intermediate, we can have a sliding, so the grain do not rotate and mostly slide, and another is when the fluid flow is very strong with a high turbulence, then the flow can pick up sediment directly vertically. So it is not clear that we can describe all of these mode of transport with unique parameters, but engineers consider unique parameters. So okay, it's a long topic, but it's still interest, in particular close to structures. So here it's a picture with maritime engineer application, like offshore platforms, pipelines to transport data in optical fiber, but also energy like gas and oil. So, but also coastal erosion, which can be protected. And nowadays, sometimes, because coastal protection are, in a sense, quite old, they suffered from coastal erosion themselves. So here, the danger can be high pollutions, in particular if we break the oil pipeline. It can be also dramatic for communication if we have optical fiber collapse. And we can also have economical impact and societal impact when a coastline is eroded. Another more recent phenomena in France showing that erosion can have very short duration, have long range, and very large effect So here is a hurricane in France last year, and creating very huge precipitation in the border with Italy. This huge precipitation give rise to flash flood with a very strong flow intensity that erode this village. Here you can see a bridge collapse. You can see road damaged, and also buildings. So, and this damage only took place in few hours. So, of course, this phenomena is related, in a sense, to climate change, and that was not and is prone to be more present in the coming years. So here is another picture showing erosion, local erosion close to hydraulic structure like a bridge, and in particular, it is well known that most of the hydraulic failure to bridge are mostly due to hydraulic flow. So here, this slide is also to give you a brief description of the process behind the fluid, structure, sediment, triple systems, showing the flow. It's here a current or a river flow interacting with a pile of a bridge, and the flow is deviated, interact, create vortices that can be strong enough to remove sediment and create scar erosion. So this typical picture have interest for different type of constructions, monopile, multipile, also pipeline, as I explained you before, but also coastal protection like seawalls or coastal dikes. Here, in general, in natural environment, we can have many type of sediments, sand, clay, but also gravels. We can also have vegetation covering that sediment bed. And there is a huge variability in sediment in terms of density, organic contents, minerals, and that material can have different states, saturated or not saturated, or not fully saturated. Flow conditions are also very diverse in nature. That can be waves, current, and interaction between wave and currents is very difficult. And so the system is very have many parameters, and the physics is still very complex and challenging to describe in both mathematical and physical approach. So here are the general methods to study erosion. That can be mathematical with computational fluid dynamics approach. Here the challenge is to capture or with high resolution the fluid structure interactions, the turbulence of the fluid particle interactions. We can also use physical models. Here we have a challenge with similitude, with scaling. So I will detail later in this talk in terms of fluid similarity with free surface flow, or Reynolds similitude for turbulence or forces on structures. I can also describe other similitudes for sediments or for air bubbles, for water and bubbles. Of course, there is a field survey, which is very expensive, but which is important for applications. This part will not will be not detailed in this talk. Here in our lab in Canada, we have very important facility to measure at fine resolution physical model. I want to show you that animation just to show you the oh, maybe it's already no the facility oh wow, not this sorry. Oh, I have a trouble, but can you see?
No, no, we cannot see. Maybe because you are only sharing your presentation.
Okay.
Okay.
Okay, here. So for instance, this is our large wave flume, which can generate realistic waves. And here is a demonstration of a wave impacts on vertical wall. Here the wave is around 2 meters high. The period is around 3-4 seconds. And in this study, we measure pressure here with at different points, and also the overtopping flow discharge to access coastal flooding with high waves. Okay, here I need to share this again. Can you?
Yes.
Okay, sorry. Thank you. So just some slide, just 2 or 3 slides explaining in theory why the interface is a big question. With a fluid sediment, we can consider, or we can roughly assume that we have a fluid over a sediment bed, which can be considered as high viscosity fluid, for instance. So, so the mechanism of erosion can be seen as a problem with 2-layer fluid having interface and adding some kind of perturbation will create undulations. So in fluid mechanics, we have very fundamental instability, which are called Taylor-Rayleigh and Kelvin-Helmholtz instability. So I will only describe this in 2 slides. So, so this slide is to give you some notation when we have a high-speed fluid with density ρ1 that flow over another fluid having different density. So here is a mass conservation for potential flow. Here is a motion equation or Bernoulli equations And this is the interface equation from the fluid 1 side. We have the similar equation for the fluid 2 side with mass conservation, motion equations, and interface. Here to demonstrate instability, physical instability, here we consider a very simple case, a theoretical case with potential flow, irrotational flow, and semi-infinite media. So linear stability analysis, that is a useful method for physicists, but also for mathematicians, consider the stability around a base flow and analyze perturbation which has a waveform. So this is a waveform propagating along x with the phase velocity omega divided by k. And here we make some analysis on perturbation by linearizing the previous systems and obtaining this matrix relating the linearized equations in terms of perturbations, and we measure, we derive dispersion relations as a condition of nullity of determinant of that matrix. And this is a classical dispersion relation for the previous system having one fluid 1 over another fluid 2. And here we describe here instability having a Kelvin-Helmholtz shape. So here we have a liquid 1 moving at different speed compared to liquid 2. The shearing at the interface will generate a wavy shape of the interface, which will grow with time. Another instability between interface. Okay, you can see, for instance, water here and sediment bed here. You can also make analogy with air and water. So this is waves, water waves. This instability is, for instance, if you have same velocity between fluid 1 and 2, but a different density, and in particular, if you have a heavier fluid over lighter liquid, then we have instability, gravitational instability. So fluid 1 is pushed downward, and lighter fluid want to go up, forming some kind of fingering like this. So this is Rayleigh-Taylor instability. So in our system, we have we can also find this kind of instability if you consider salt water and light water, or and also sediment and water. Here is a picture of instability at the interface between water and sediment. Here we start with flat bed or almost flat bed. This can be seen as perturbation. And if we impose wave and create some typical perturbation like this, with time, we will see that the perturbation which propagates from this nucleation site, and also pollute the whole systems. Here are also other instability that we can observe with waves, starting from flat bed. We can have ondulation like Kelvin-Helmholtz, but with sediment. And here is only 2D. And we can also generate 3D instability pattern, like 3D vortex ripples, and also this kind of more regular pattern with shape brick as a brick. So this is to explain you the context, the background of the fluid, sediment, and structures. So now, with this part, I would like to present the numerical approach that are available to deal with that kind of systems, and also physical approach to model in lab this kind of system. So here is a general principle of all of numerical methods dealing with mobile beds undergoing erosion and deposition under flow, which can be current or waves. So we usually start from a geometry of the system to compute the flow. From the flow, we compute or we derive the friction or the fluid particle fluid sediment interactions to compute the sediment transport. From sediment transport, we localize zone of deposition and zone of erosion that change the geometry, and we loop next step to change the hydrodynamics that will change the sediment transport and also change the geometry and so on. This loop is very similar to instability. Okay, this is the same engine of instability at the water sediment interface. We start with initially flat interface. We impose hydrodynamics, which destabilize the interface. Destabilization of interface will generate ripples and waves that modify the flow, and so on. So here in this part, I will talk about the different approach to compute that circle. In particular, the single phase or the two-phase model, the different treatment for turbulence with the classical and mostly considered by engineer the Reynolds average Navier-Stokes, and other advanced turbulence modeling like large eddy simulations and or direct numerical simulations. I will also discuss modeling assumption with model computing or not the free surface or the waves, in fact, and also a different model that are classified into hydrostatic or hydrodynamic pressure. So to start, this example shows adaptive meshing because the fluid domain evolved with time during erosions. So this is an example with pipeline on seabed. So during erosion, we have sediment removed, so the interface change, and by consequence, the liquid domain change over the time. So one technique is to change the computational domain for the fluid dynamics with time by using remeshing or adapting the mesh. So this is an example here. Another example is the 3D case showing a circular pile submitted to waves. Here we compute the scar hole in blue and the deposition in red. So in this approach, we have not so bad results for numerical model. I will explain you later why I consider this result is not so bad. Of course, for mathematical guys, I think that people can see a very large difference, but I will explain that there is a many uncertainty in physical parameters that make that kind of results acceptable. This is another example, but in a mesh-less Lagrangian model, which is called SPH. This flow, this configuration of flow is you have a river flow here. You have a weir. So the water diverges from upstream to downstream. The water diverges like this, form a jet inclined to the bed. The water jet impacts with inclined angle an initially flat bed, and then the jet is deviated by the bed. So during this, we have normal pressure of water to the bed, and also shear stress at the interface that removes sediment. And from initially flat bed, we have evolution on the erosion with a deeper scar hole and higher dune or deposition zone. One of the very computing expensive technique is to directly compute flow field as classical by Eulerian code, and having a Lagrangian description for each sediment. So this is called the CFD discrete element method. Here, the main idea is to use Newton laws in a Lagrangian sense approach for each particles, and computing all the force of the surrounding grains. So one limitation is the number of particles, and also even though it's very accurate at the granular size, one important limitation is the character of sediment which need to be monodispersed here and well-shaped or spherical shape. Of course, we also need to introduce physical parameters to model contact forces between particles. And that can explain some discrepancy with real experiment. In my lab, we are using a two-fluid model, which compute both part of the liquid. We have a one layer pure water or clear water, and one layer with sediment fluid like this. And we compute, in this case, jet impingement on interface. And we did in the past shearing of fluid 1 over fluid 2 and obtain a nice Kelvin-Helmholtz shape. We also applied this kind of model for scouring. Here we have a cylindrical pile subjected to river flow. Here is a description of streamline with a high vorticity in the wake region, and also some Horseshoe vortex just upstream of the cylinder. So this is now a moment to talk about a physical model. After describing the mathematical model that is can be used to deal with fluid structure and sediment problems, here is existing facilities. This example is experimental facility in UK, showing a study on coastal structure like dikes, protecting harbour. Same lab showing half cylinder subjected to waves to simulate offshore wind farm. Here you can see the magnitude of erosion, of scar erosion at the vicinity of the pile. This example is my previous lab in France, showing design, conception of dikes and design of armor blocks along dikes for cheap defense in coastal region. And here another famous lab in Netherlands showing multipile subjected to waves. So in all of that experiment, we need to fulfill requirements to upscale measurements to natural conditions. And this is done by strictly respecting scaling rules, which are mostly the Froude number. Froude number is defined like this, as ratio between velocity to critical velocity. There is a connection to Mach number for compressible fluid like air. And another important parameters is to characterize the turbulence is a Reynolds number, which is a ratio between the velocity times unit length, length scale, to viscosity. One difficulties in coastal or in hydraulic engineering is the compatibility between both similitude. As we demonstrate, as we know that for water, Froude number and Reynolds are impossible to fulfill together. So the only conditions to respect both scaling is to change liquid, which is not very easy for large facility. And the other is, of course, having scale reduction equal to 1, which is also not convenient for laboratory conditions. When dealing with structures, we have to also consider interaction between waves and the structures. So in particular, you can have diffractions, you can have a different pattern in the wake regime. So in this case, we need to fulfill another non-dimensional number, which is called Culloden-Carpenter, showing the transition between the drag and the inertia, mostly. When dealing with waves and breaking waves, the condition of aeration of the wave during the breaking is also play an important role. As you may know, a small amount of air bubble in water make the water compressible. So small amount of air bubble can change important property of incompressibility of the liquid of interest. So here is an example showing the bubble effect during wave impact. I show you. In particular, the interaction, the momentum transfer of force to the air bubble, which reduce wave impact on the wall. So, of course, if we deal with sediment, we need to consider scaling of sediment transport. And this is done by considering the Shield number similitude, which express the entrainment force by water to the stabilizing force on sediment, which is mostly gravity. Here is a diagram showing the critical number for erosion. So above, we have erosion. Under, we have no erosion. So, but recent study present different curves depending on the mode, rolling, sliding, or lifting mode of transport. So in particular, we can have slow motion below the classical critical curves during the rolling mode, and this is mostly I will explain that this is mostly one reason why condition to motion is not so accurate. Here, for instance, you can see that above from criteria, we can have 2-3 order of magnitude between the theoretical critical value and the other criteria if we consider rolling, for instance. So now I can shift to ongoing study in my lab. So this symbol is found in Quebec, close to road. It means that if you drive your car, you can be submerged by extreme waves. This symbol explains why Ministry of Transportation have a big interest for coastal erosion or coastal floodings. For instance, this picture was taken in Quebec during tropical storm 10 years ago, showing extreme waves overtopping the coastal defense with a big risk for driver. And here picture are post-event photography showing damage on the road. Coastal wave can also transport debris like wood or rocks. And this generate very costful reparations. And of course, with climate change, sea level rise, extreme scenario increase. So ministry are interested in protection to protect this kind of roads. Here also other picture showing erosions near infrastructures or structures. If you see such kind of landscape, you can clearly see erosion like this. And so in that case, usually erosion starts at the toe of the embankment of the structures, and by regressive process damage the whole process. So this is why we conduct for ministry different investigation on wave impacts to coastal structures like seawalls, but also on dikes. Here, today I will talk about seawalls. So we did experiment in our large flume, which is 100 meters long, 5-meter width, and 5-meter depth. Here we use a piston-like paddle to generate wave up to 2 meters. Period of wave can be up to 12 seconds. And we can also generate solitary wave like tsunami. In that case, okay, I show you the facility. Here the scale of the model was 1/2, so it's very close to natural scale. And for the construction, we had a big team to construct the wall with instrumentation of 25 pressure sensor to measure at very high frequency, 100 kilohertz, the impact pressure of waves to the wall. We also make the velocity measurements and measure waves as well. Here is some picture of the wave. It was not easy to measure aeration of the waves. And we also measure below, behind the water overtopping the coastal structures. Here's typical examples of type of waves impacting the waves, having or not air bubbles. And we did analysis on pressure in relation to aeration of breaking waves. So here is a result of pressure impact to the and depending on low aeration or high aeration. So we mostly identified two kinds of pressure signature to the wall during wave impact. One is high pressure for low aeration and low pressure with a lot of bubble entrainment. So remember, if the flow is doesn't have air bubble, the liquid water is incompressible. But with a given amount of air bubbles, water is compressible. So that huge difference can explain why incompressible water have more pressure impact to the wall than aerated or compressible water with bubble. So this is important because if we want to reduce force on the coastal structure, it should be interesting to build a breaker in order to maximize the presence of bubbles in wave before it impacts the wall. Another picture is to see the duration, the peak duration. So between incompressible no air bubbles and compressible water with bubbles. As you can see here, the peak is very short with incompressible compared to peak of pressure with compressible water. And with compressible water, we also find oscillation here. That is not observed for compressible water. So here is a diagram showing the experiment, the main results. So short peak duration with a very high pressure on the wall for non-aerated waves or incompressible flow, and long peak duration but low pressure on the wall for broken waves with bubbles. Here is an explanation of the oscillation that we saw here in terms of interaction between bubbles and waves. So large pocket of air can collapse and form smaller and smaller bubbles that create such kind of signal. During experiment on impact wave on vertical seawall, we systematically observe scarring at the toe of the vertical wall. And the ministry was particularly interested to more understand the mechanism and the depth magnitude here because of the stability of the coastal protection. In particular, this image presents some basic mechanism during the wave impacts to vertical seawall, showing the ascending jet forming a splash and an impinging jet to the bed, forming a scar hole here. Of course, if the scar depth is deeper than the foundation of the coastal protection, then we can have a risk of collapse of the protection itself. So this is why we focus study on this kind of phenomena.
Sorry.
Yes.
Sorry. You only have a couple more minutes.
Okay. So just go to yes. Interesting part with sediment transport research in our lab are the measurement of bed forms or instability pattern at the liquid and sediment interface. And in particular, we measure the formation and the migrations and maturation of the wave of the interface in order to compute and to validate numerical model like this. So to conclude, I will recall that sediment transport is still a very open problem, open questions. The main difficulties are the interaction between one phase liquid to another sediment. This interaction, this complexity is enhanced if you introduce structures. So in particular, Mario, my student Mario will give you some results on numerical model. And there is a different approach to deal with that problems. One is computational, which require physical parameters. I explained that physical parameters are sometimes uncertain, and sometimes they present large errors, in particular for motion criteria, because behind it can depend on the mode of transportation, rolling, sliding, or lifting. And one difficulties in numerical model and also in physical experiment is the role of turbulence that give perturbation at all frequency that can destabilize the bed. And about the ongoing research efforts we are doing in my lab is large-scale experiment with a large wave plume, and also numerical investigation on scar erosion. And every year I have some opportunity for students for master or PhD program in my lab. So thank you. Some reference here, some very state-of-the-art book here on mechanism and scar engineering manual, and some very focused conference on scar erosion here. So thank you.
Okay, well, thank you very much, Damian. We don't have more time for questions, but I would like to emphasize to the students who are listening right now that you have this financing program right now for master and PhD, and particularly I want to point out, like, this is a direct financing for you, so that's basically you only need to send your CV to Damian, and if he approves that, you get this master program or PhD program in his institution. Well, I would like to thank you very much again for this one, and certainly we will have questions, but people will contact you.
Okay, thank you very much.
Thank you very much, and thank you everyone for watching us.
Okay, bye.